y'all, Darrell Lee Berry Jr. here, back with some physics. Excuse me for being a bit later than scheduled. I won't be here long. I'll just look at the problems that I'm doing for this week on the Virial theorem. So those who've been watching regularly, you know I derived the Virial theorem a few days ago, something like that. So basically, looking at a problem with applying the Virial theorem to Hooke's law. So I got some notes from my professor on it, and I'll take a look and see if I can perform the task on it. It is looking pretty difficult. We'll see how it goes. So my first trial didn't work out. That's the book with the Virial theorem right there that we looked at before. So from what I got from my professor is, so let me copy the Virial theorem down again. I'll get it directly from the book. So we're looking at this. So we have the average value of T, the kinetic energy, is -1/2 equals -1/2 the sum of the average, because the Virial theorem is basically dealing with a system of particles. The force of all the particles added together, dot producted with the position of each particle. Let me get this real fast. So this is actually what always comes to mind when I think of the Virial theorem is Zwicky, an astronomer who was instrumental in, if I remember right, dark matter, discovering dark matter. And one of the things he utilized was the Virial theorem, some application of it. So it has many applications. It comes, I believe, ultimately from this man named Clausius in thermodynamics. And the theorem was developed and applied to many other things now. So now we know that the Hooke's law is F equals -k, where k is the spring constant, and x is the distance through which a mass on a spring, let's say, is moved. Matter of fact, right now we're dealing with a mass on a spring. Let me copy this down. So I'll try to start this problem fresh with the tips I got from my professor. I skipped one of my extra pages. Right? So basically, showing that it holds for Hooke's law, spring oscillating in one dimension. So this would be our X. This would be the spring. And so what I need to do is actually apply the Virial theorem to this. So utilizing Hooke's law, X is going to be A cosine omega t minus, we'll just say phi, whatever initial shift I give it. And professor was saying we can consider phi equals 0. So X equal the amplitude cosine of omega t. So the force would be -kx, which means the force would be -k a cosine omega t. So one thing she mentioned was, which is a concept I'm still getting used to, in um, differential physics or integral physics. Apparently, you can get the average of some quantity by dividing it by tau and taking the integral from 0 to tau. And let's call this the average of I. So the average of whatever the quantity I is the integral from 0 to tau of I divided by I. And it's similar to the idea of, if we have so many numbers, 2 plus 3 plus 4, we have to divide by 3 to get the average. And we add them up, divide by how many numbers it is. And what is that? 9 over 3 equals 3. And as you can see, the average of these numbers is 3. So this is the idea. So it's like this is sort of the analog to that, dealing with integrals and dealing with a certain quantity that we're getting the average of. So that's part of the issue, part of what we're looking at. So, I forgot about potential. Okay. So, right, need to go back to force. So, an interesting thing about force is, and I need to do this derivation one day because I can't remember exactly where it comes from. The force equals negative the derivative of v, with v being the potential. So F is the force and v is the potential. So we have, let's say, not sure what a good situation is. Well, I guess gravity. We have an object orbiting around a central force. The distance from the object will give a potential. It's like how you have an object above the Earth, it has a certain gravitational potential, and the potential is related to the force that's pulling on it and giving it that potential. And this is the relationship that you have between the force that is acting on that potential and the potential itself that's imparted by that force. And I wonder if it's even related to the force, like if the object falls, like when we drop an object to the earth and it hits the ground, does it relate to the force of the impact? I'm not sure about that. But the actual potential that it has, if you take the derivative of that with a negative, then you get the potential. So if force equals negative kx, then it'll be partial x and negative kx. So, hold up, I'm looking at this backwards. Let me think. Okay, yeah, I have to swap it. They want to give me the right answer. So we actually have the force. I have to take the integral of both sides. And so that means that the potential equals the negative integral of force. And since our v is related to x, because our force is only along x, our whole system is only along x, that means I'll be taking the negative integral of negative kx dx, which equals, so the force is negative, you have to take the negative of it. The k is a constant. So we have x squared 1/2 and plus a constant, but we always ignore the constant. And if any of you who have a question about the integral, if you need a refresher on integrals, let me know. And if you have any other questions as well, I'm monitoring the live chat to see if anybody wants to have a discussion. Have any questions, any comments, or just to say hi. Make sure you like, subscribe if you haven't. I'll give it to 1,000 subscribers. So we have that. So this is the potential in X. So let me see if I can remember how this relates. The potential is negative 1/2 kx squared. X is that. So x squared would be a squared cosine squared omega t. So now we have the potential and the force in terms of x. X is negative k a cosine omega t, and v is 1/2 a squared cosine squared omega t. So take a look at this. I'm just going to copy this down, see if I can get a better bird's eye view. Now we have the force in terms of potential, and vice versa, depending on if you do an integral or derivative. And we have both of those in terms of sine, cosine. If I were to simplify this utilizing our understanding of what a dot product is, I can call this the magnitude of f, the magnitude of r cosine theta. And since it's in one dimension, we know that cosine will be either of pi or at least a pi, 0 or 0 or pi. So it's the same thing as saying negative 1/2. We only have one object. So negative 1/2 f r because theta equals 0. And equals negative kx. Why don't I write this completely? So that means we have 1/2 and I believe this would be would that be a unit vector? Yeah, let me add one more step here. So I believe this would be negative 1/2 some I f I actually will go fr I hat dot I hat. Actually, I hat dot R hat. If that's a unit vector, which I believe it is, but we'll see. If the answer comes out wonky, then it might not be. I remember something that we did in one of the EM classes at a great EM professor that I LA'd for, that I was a learning assistant for. And he really hammered home the shortcut you do with the dot product with cosine. And this is all in one plane going in the same direction. I mean, it could still be pi or 0, depending on what the mass is moving outward or inward, but it's fine to just say 0. We only have one thing. And so we have negative 1/2 negative a cosine omega t, which equals negative 1/2. Let me make sure I didn't drop a negative. Yes. Equals negative 1/2 k a squared cosine squared omega t. So this will give me negative 1/4 k a squared cosine squared omega t. And this needs to equal, the average of each of these needs to equal. All right. So let's try the integral thing and see how this works. So I have 1 over a period of negative 1/4 k a squared cosine squared omega t d period. And professor was letting me know how if I take the right, and let's actually fill in for kinetic energy. So we have integral 1/2 m x dot squared 1 over tau d tau. So basically I filled in for what kinetic energy is in one dimension. And we have the average of each. So I need to get x dot have x squared x dot the time derivative. So whenever you see a element or expression in physics where there's a dot over it, it's a derivative by time. So x dot is dx over dt. And if you see a prime, like x prime, that's usually a derivative over something else like dy dx. But I actually like to put prime dots on everything because the primes is, although this seems to take up a lot of space and interfere with things. Like if you have a exponent on your x prime, then you have look like exponent of x12 or whatever. So I always like to do it on both. So what we have now is negative a omega sine omega t. So I'll go ahead and plot this down for x dot. And if you need a refresher on derivatives, let me know. Make sure I didn't miss anything. And I'll add one more step here as well. We have 1 over tau integral 1/2 m. Oh crap, and I have to square it too. So if I square x dot, it's going to be a squared omega squared sine squared omega t d tau. And that's supposed to equal 1 over tau integral negative 1/4 a squared cosine squared omega t d tau. All right, so utilizing the shortcut my professor gave me, so to explain what's going on here, if you have, so we started with, well, let's do each of these. In fact, both of them are squared. Squared, squared. All right. So if you have, let's say, cosine x, it'll start up here somewhere, go down, and come up here for one period. So the average of this is similar to if you had negative 2 plus 2 divided by 2. That's 0 divided by 2, so the average is 0. So you have a negative here and a positive there of the same value. Oh, and I need to put my x-axis up higher. So it looks something like that. Average is 0. And however, if we have cosine squared of x, all of the negative values will be flipped to positive. So it'll look more like this. So basically the part that would have been underneath is flipped up. So basically this point here is, still crosses 0, 0, 0. But it flips up in the middle. It looks something like that. So the average, she's saying, is going to be 1/2. And this one is not as clear to me. So I see. It's because equilibrium is still the same. So in this case, equilibrium is the x-axis. But in this case, equilibrium is here. So both of them are positive. That seems like it should be 2. Let me actually put what we're using here, tau. Why is that 1/2? Let me think about this. So this is 1. Oh, I see. Because if that's 1 on the x-axis, really this is 1/2 from equilibrium, and this is 1/2 from equilibrium. So I guess that's what makes the average value 1/2. I have to think about that more though, but it seems related to that. All right, so she was saying that this integral should be very easy for that reason. So let's look at this. So I'll bring out the constants to make this a bit more clear. We have 1/2 ma squared omega squared integral 1 over tau sine squared omega t d tau equals, so we have negative 1/4 a squared integral 1 over tau cosine squared omega t d tau. So everything out there is constant. So I believe what she's saying is, since this is a average of the square, that'll be 1/2. So now we have 1/2 ma squared omega squared times 1/2 equals negative 1/4 k a squared times another 1/2. This becomes 1/4 ma squared omega squared equals 1/4 k a squared. Oh, 1/8. All right, the a's cancel, so we have 1/4 m omega squared equals 1/8 k. Right. At the moment, I'm not seeing how this works for the Virial theorem. Oh crap! Hold up. 1/2. You notice this is the kinetic energy on the left side, basically. 1/2 m. I mean, close. It's like the angular. No, no, no. Omega is the default frequency, the angular frequency. Oh, so check this out. I see it. So what's going on is, so if you have the spring constant, that is newtons over meters. So I realized this yesterday because I always forget. I guess I'm not going to forget now because I have to know it for grad school because we have to do things in more detail. But I was doing a problem yesterday. I don't remember what problem it was. Might even been for foundations or reviewing all of undergraduate stuff. And I realized that I needed to solve the problem. Matter of fact, it might have even been the exam, the foundations exam I did. I did all right on the exam, but there's one problem I had to solve for a sort of complicated angular problem, which you all know I practiced on. I did an angular problem for you all, so I actually did that problem really well, and I got it. But I had to end up getting the spring constant. It was like a crazy problem with gravity and springs. There was like a few things in there together. And what I found was that when I saw for the spring constant, I remember it being kilograms per second squared. If I remember right. So that's what I thought the units for it was. But then when I looked at a textbook later, I saw that it was newtons per meters. And you might wonder, how is that equal? Well, if I multiply this by meters over meters, you can always multiply things by 1. Newtons equals kilograms meters per second squared, and then we're divided by meters. So this does equal kilograms over second squared times meters over meter. You see that? So the spring constant, like any spring that you have, if you have a spring problem. Matter of fact, the lab I'll be leading on Tuesday, so I'm a teaching assistant for a mechanics lab. So pretty cool. Then I'm taking a mechanics class, even though it's graduate level, so we're not doing anything I'm doing in there, but it does, as an aside, it does reinforce the fact that I've learned my undergraduate physics because, usually I'm too busy to review the lab in detail. So I just go in there, and when they ask me questions, I just have to answer the question. And I find that I'm able to, work out the stuff on the fly. Usually I might have a typo on one of my formulas or something, but as I go back and help people on undergraduate stuff, I'm like, okay, yeah, I'm able to work that out and figure this out and solve for, because in a lab, you're actually doing stuff with devices. Like this last week, they were measuring the acceleration and velocity and position with a cart going on a ramp, and we're getting the angles and all of this stuff here, and getting the angle based upon the acceleration of the ramp and things like that. So we had to work that out. All right. So looking at this, what this means is that K. So let me actually write the units here. So M omega squared is going to be kilograms radians per second squared, and K is going to be kilograms per second squared. All right. And this is all in solving this problem. So what that means is these are equal, except for the right side is 1/2 that. So the interesting thing is, so let me write it this way. 1/4 M omega squared equals 1/2 1/4 A. So now we have 1/4 kilograms 1/2 squared equals 1/2 1/4 kilograms 1/2 squared. So unit-wise, we can see that the Virial theorem is working out. So it's basically 1/2 of the right side in the same terms, but I mean, not the exact same terms, because this is the angular frequency and the mass, and this is just the spring constant itself. But we can see that the units work out so that they're 1/2 of each other, which is what the Virial theorem is saying. So going back to the Virial theorem, we have the kinetic energy is 1/2 of this thing over here. Excuse me, the kinetic energy equals 1/2 of the other thing over there. And this relates to another form of Virial theorem we'll take here. I remember probably looking up a video on it. the kinetic energy is 1/2 U, which is probably why she wanted me to get U. And where did I input U at? That's right. I took the integral of F to get U, and thus I can replace U with, I can replace F with V, because it's the same thing, as long as I put a negative on it. Craziness? And let me highlight where I put that at. Let me clear up my highlights. So basically, I took this equivalent here, Vx, put it in terms of the solution to the Hooke's law in terms of sines and cosines, and then I substituted that here. All right. So I shall consider this problem done. I told Professor I'll work on it and go see her and ask about it. I actually worked on another problem as well, which is a whole lot harder. That was what I was doing earlier. It's probably one reason why I was a bit late, because I was doing this all day. I lost track of time. I was just taking a breather because I was like, damn. So basically, this problem, it's kind of from a textbook I recall. I don't remember which number it is, but it's dealing with orbits, orbital mechanics, and basically it's a problem asking if you take a particle that's undergoing a circular orbit, don't know how it's doing a circular orbit. It's like more like a thought problem, really. Which I expressed to my professor. I was like, man, this problem is crazy. She was like, all right, good thing to think about. Help you to understand some things. But the particle is apparently moving in a circle. Let's have a circle there. But then it's being affected by a force, which is this force here, at the edge of the circle. So the force is not in the center, how we would normally think of it. The force is at the edge of the circle, affecting the particle somewhere on the circle. And then we have to calculate, first we have to show that the total, let me confirm it. Just going to got to confirm that the force on the particle is proportional to 1/5, to the fifth power of the radius. So that's what we have there, the radius of the fifth power. So, but now I'm working on the second part, so, which I haven't figured out yet. I don't remember what we have to do. I think we have to show that the energy equals 0, the energy of the particle. It's an ugly problem. All right, y'all. We're seeing you all today, everybody who popped in. Hopefully you enjoyed. Like if you haven't, subscribe if you haven't. I'll be back, of course, next week. I'm not sure if I'll be back tomorrow. I'll see. But I'm sure I'll be back during the weekend. Of course, I'll make sure to start posting more regularly. So not every day, at least every other day. So thank you all for popping in. Hope you have a good evening, and I'll see you all next time.